Hello, so in this video I'm going to go over example 8, which we did in class, but I think is worth doing again. And example 8 is the first example of limits with constraints. So in example 7, which hopefully you saw and made sense before you watched this video, in example 7 we had this nasty function sine of 1 over x, and we wanted to get rid of it. And what we did is we knew that we could replace it out by something that is bigger than sine of 1 over x. And we used sine of 1 over x as always less than or equal to 1. Or you could use something like sine of 1 over x is less than 1.01. All of these strategies will work. So that's what we did in example 7. We had something nasty. We bounded it by something that was bigger. In this example, we're going to do the same thing. And it turns out the nasty function is going to be absolute value of x plus 3. And so we're going to want to find something to upper bound square root of x plus 3. Square root of x plus 3 is less than something. And if we do that, then we can replace it out just like we did in example 7. But there's a problem, which if you draw the graph of x plus 3 and you compare it to the graph of sine, so the graph of sine of anything will always bounce around between 1 and minus 1. That's the graph of sine of 1 over x, something like that. So it's always between minus 1 and 1, and that's why the absolute value was bounded. Whereas absolute value of x plus 3, the graph of x plus 3 looks something like this, and it just goes on forever and ever. So in the graph of sine, you can sandwich it between minus 1 and 1, and then that's how we got our bound. That's how we got this 1, or if you want, this 1.001. But in the graph of x plus 3, there is no way to sandwich it between any number. So that's a problem. And what we're learning right now, limits with constraints, is a way to get around this problem. And the way is, instead of looking at all possible x values, we're going to limit our scope to just looking at some x values. And we're going to make the epsilon delta proof work with that limitation. And when you do that, it's going to also make it so that we can bound the function x plus 3. So in some examples, to ensure that the delta we find depends only on epsilon, a given number, and not on x, which is a variable, to ensure that the delta we find does not depend on x, we must place additional constraints on x. Okay, so I think the best way to see it is with an example. Prove that the limit as x goes to 3 of x squared equals 9 using the epsilon delta definition. So the first thing I'm going to do is write down what does this even mean? What does it mean for limit x goes to 3 of x squared equal 9? It means for all epsilon greater than 0, there exists delta greater than 0. So that what? And I'm going to write it backwards. I'm going to write the conclusion first, because when I do the proof, I'm going to start with the conclusion. And so I'm going to write the conclusion first. X squared minus 9 has to be less than epsilon, and that has to happen whenever x minus 3 is less than delta and bigger than 0. So that's the thing we want to show. That's what this statement means. And now we're going to prove it. So what do we want to show? Let's see what we're given. We're given epsilon greater than 0, and we want to show that can find delta greater than 0, so that x squared minus 9 less than epsilon whenever 0 less than x minus 3 less than delta in absolute value. Okay, so we're going to start with the x squared minus 9 less than epsilon, and we're going to try to eventually make our way to x minus 3 less than delta. So that's our goal. And the first thing to realize is to keep your eye on what you're trying to look for. We're trying to look for an x minus 3. We have an x minus 9. How is x minus 9 related to x minus 3? The answer is you can factor x squared minus 9. And in fact, it's a nice difference of squares. So it's a quadratic equation that you can factor. And in fact, it's a difference of squares. So you can factor it as x minus 3 times x plus 3 less than epsilon. So those are the same. So we're just doing algebra. That's a reversible step. And now, okay, I have x minus 3 inside the absolute value, but I would like x minus 3 outside the absolute value. So why don't I just take the absolute values out? X minus 3, x plus 3, less than epsilon. Okay, and now we are in the same exact kind of situation we were in in example 7, where we have what we want, the x minus 3. That's what we want. But we also have some nasty junk, the x plus 3 in this case, that we need to get rid of. And you can't simply move it to the other side, because if you end up with epsilon over... So maybe I'll do it again. This is what you can't do this. It's tempting. It's tempting to do this, to say x minus 3 less than epsilon over x plus 3, and then set delta equals epsilon over x plus 3. So this is tempting, but don't do this. This is not what you want to do. And the reason is because if you did this, delta would depend on x, and that is not allowed. So in what we're trying to show, we're trying to find one value of delta. So given any epsilon, there's exactly one value of delta that works for all possible x's that would satisfy this. So you can't have delta depend on x. That's not what we're trying to do. So if you do this, you haven't shown the thing we're trying to show. So that's why this doesn't work. So that is why we need to find some way. We need to find some way. We need to find some way to bound x plus 3. And we know from what we talked about in this thing we defined, the left replacement rule, that what we actually want to do is we need to make a lemma. So a lemma is like a little side argument that we're going to insert into our main argument. And our lemma, because x plus 3 is on the left, what we're going to do is we're going to bound x plus 3. So if we can get x plus 3 less than some bound b, less or equal b, then we'll be good, because we can replace, then we'll be able to use the left-hand rule and replace this with a b, and then we'll be in business. So that's what we're trying to do. We're trying to find a bound b for x plus 3. Okay, maybe I'll erase this so we don't get ahead of ourselves. All right. And in example 7, we had the sine function and b equals 1 worked. And that was just a fact about sines. But today, in this problem, there is, unfortunately, I can tell from the graph that there is no b that is going to make this lemma true as written. There is no b that will work. So the graph of x plus 3 looks like this, and it just goes on and on forever and ever. Is there a b value that I can draw, like if I draw y equals b over here, that will bound the function, that the function always lives below? No, it's gonna always escape. So there is no b value that will make this work as written. And so what we're gonna do is we're gonna restrict our attention to a small interval. We're gonna restrict our attention to a small interval. We are going to assume, and here we're going to make an assumption about what delta is going to be. Remember, it's our job to find delta. So if we want to, we could assume that delta is, say, less than 1. Let's assume that delta is less than 1. And if delta is less than 1, then the hypothesis of our problem tells us that x minus 3 is less than delta, and delta is less than 1, so x minus 3 is less than 1. And so we can use that as part of our lemma. So our lemma is not just going to say x plus 3 less than b. What it's going to say, if x minus 3 is less than 1, then x plus 3 is less than b. And so this extra part, this is called a constraint. We're only looking at some x values, which we're going to have to justify this assumption on delta. But by looking at only some x values, we can find a bound on x plus 3, which is what we want. So, and you can see this from the graph again. So let me draw the graph one more time. So the graph of x plus 3 looks something like this. And it's true, it goes on and on forever and ever. But if you look at x values that are close to 3, if you only look at x values that are close to 3, then the function kind of is well behaved. It's not blowing up or anything. So that's the picture proof of what we're doing. We're going to look at x values close to 3 and get an upper bound on what x plus 3 is. Okay, so let's try it. And again, I don't want to presuppose what b is. We're going to fill it in as we go, because I won't know what it is until we get there. So here's the proof of the lemma. The proof of the lemma. So I'm going to start with x minus 3 is less than 1. That's the hypothesis of the lemma. And that is the same thing by the sandwich property, minus 1 less than x minus 3 less than 1. Okay. And now I can rearrange this just for x. So I can do 2 is less than x less than 4. Okay, that's nice. And I want to end up at x plus 3. So why don't I add 3 to both sides? 5 less than x plus 3 is less less than 7. Okay, so that's what I have. And really what I would like is I would like x plus 3 less than b. That's what I want to get to. By the sandwich property, x plus 3 is less than b is the same thing as x plus 3 is between b and minus b. And I'm really close. So I have that x plus 3 is between 5 and 7. And I'm asking myself, is there a value of b I can come up with so that being between 5 and 7 definitely means you would be between minus b and b. So on a number line, between 5 and 7 looks like this. So 5 to 7. And on a number line, b between minus b and b looks like this, right? You got let's label numbers a little better here. 5, 7, 0 somewhere here. We'll say this is b and this is minus b. So is there a possible value of b so that the green zone between 5 and 7 is definitely included in this, what I've drawn in blue, which is between minus b and b? And I think as long as b is bigger than 7, this is going to work out. So if b is bigger than 7, then everything between 5 and 7 is included in the range from minus b to b. And one particularly nice example would be if just b equals 7. If you do b equals 7, then if b is equal to 7, you have from 7 to minus 7. And then it's perfectly clear what we've done. We've gone from 5 to 7 to 7 to negative 7. Like we just moved the left thing, we've relaxed it by moving it down. And so if you are between 5 and 7, you are definitely going to be between. So let me erase this little cartoon that was just for thinking. If you are between 5 and 7, you are definitely between negative 7 and 7. Negative 7 and 7. If you are between 5 and 7, you are definitely between negative 7 and 7. And if you are between negative and 7 and 7, that is the same thing as saying that your absolute value is less than 7. So the whole proof works out with b equals 7. In fact, any number greater than 7 could have worked as well. But just to be concrete, we're gonna do it with a 7. Oh, one more thing. I wrote it with a less than or equal to over here. And when you do these replacements, you can always make a less than or equal to happen by adding one line. So you can say, if it's less than 7, then it is less than or equal to 7. So that's fine. We can add that in. And this was one of the homework problems about less than versus less than or equal to. That will be used a lot. So it's good to know. So that is the proof of the lemma. And the lemma is telling us that we have the bound x plus 3 in absolute value less than 7, less than or equal to 7. And that works as long as we assume delta is less than 1, because when delta is less than 1, we have x minus 3 in absolute value is less than 1. And that's how the proof went. So this proof is very similar to like the inequality proofs that you had. You just have to keep an eye on what you want, what you have, and put it all together. Okay, so that's the lemma. And now we're in good shape. So just like in example 7, we replaced sign by 1. Now that we have this lemma set up, we can replace x plus 3 by 7. So on the next line, I can write by the lemma, and the lemma is assuming delta is less than 1. So if delta is less than 1, as long as that happens, the lemma tells us x plus 3 is less than 7. And when x plus 3 is less than 7, by the left replacement rule, we can replace x plus 3 in our chain of logic with a 7. So this line, x minus 3 times x plus 3 less than epsilon, becomes x minus 3 times 7 less than epsilon. And when we're doing the left replacement rule and the right replacement rule, they are set up exactly, if you write it like this, so that the arrow goes the way we want it, which is like this. So if this part is like the hypothesis part and this part is the conclusion part. If this thing is true, then that thing is true. That's the setup of the left replacement rule. And it really just makes, like, if you think about it carefully and you understand what it's saying, it really is making intuitive sense. If epsilon is bigger than the big number 7, then definitely epsilon is bigger than the small number x plus 3, right? So because 7 is bigger than x plus 3, if epsilon is bigger than 7, then epsilon is bigger than x plus 3. So in this course, we're calling it the left replacement rule. In regular mathematics, they wouldn't even write that. They would just say, like, they would just say, like, it's obvious, or they wouldn't even write anything, and it would be, like, clear. They would say, like, because x plus 3 is less than 7. But in this course, if you want to indicate what you're doing and to make it a little more streamlined for you, you can use the left replacement rule. Okay, so we're at x minus 3 times 7 is less than epsilon. And from here, the rest of the proof is very similar to the very first proofs we did with epsilon delta. So this part should be not too bad. We want to get to, at the end, we want to get to 0 less than x minus 3 less than delta. And we always know that we can do the step of removing the 0. X minus 3 is less than delta. If you are between 0 and delta, you're definitely less than delta. That's what we've done. And so to go from here to here, we just maybe just move the 7 over. And to go from the epsilon by 7 to the delta, all we have to do, this will work as long as delta is less than epsilon by 7. So that's the justification for this line right here. So as long as delta is less than epsilon by 7, if you're less than delta, then you're definitely less than epsilon by 7. And this is a perfectly good proof. So we have started from the conclusion, x squared minus 9 less than epsilon, and we made sure to make all the arrows going the right way. There were a few one-way arrows. There was one, there's another one. And we got to the hypothesis, 0 less than x minus 3 less than delta. So this all works. It's all perfectly good. The last thing we should say is what delta is. Remember, our job is to find the delta. And we've sort of done it already. So we said delta has to be less than 1. We said delta has to be less than epsilon by 7. So to make sure that both of these things that we've used in our proof are true, to make sure that this arrow is true and this arrow is true, we just need to set delta. And we can write this. You can write this at the top of the proof. Sometimes people do that. So they'll say they'll write it at the top. Set delta to be the minimum of 1 or epsilon divided by 7. And minimum just means whichever is smaller. So another way to write delta is the minimum of 1 and epsilon by 7. You could also write set delta to the smaller of 1 and epsilon by 7. Those mean exactly the same thing. So minimum just means whichever is smaller, do that. And so by choosing delta to be the minimum of 1 and epsilon divided by 7, it satisfies both that it's less than 1 and that it's less than epsilon by 7. So because it's the smaller one, it satisfies both. And that means our proof is perfectly good. It connects the two things we want. You can also write this thing at the end. So sometimes, we found it at the end. So it's kind of like a little dishonest to go back and write it at the beginning as if we knew it the whole time. So you could write it at the end as well. Wherever you write it is good. So what are the elements you need to have in the proof? What is the delta? That's one thing. The chain of logic is the main thing, connecting the 2 points we want, the hypothesis and the conclusion. In this case, we needed a lemma to replace something, and we've justified all the steps. So we've justified this replacement, and we've justified this step here. So that's what we're looking for in a proof. And if you understood this example, you should absolutely try example 9, because example 9 is the exact same proof, but instead of assuming delta is less than 1, what we would like you to do is assume that x is within 2 units of 3. That's the same as assuming x minus 3 is less than 2, which happens when delta is less than 2. So example 9 is a really good one to try, because if you understood what we did in this video, example 8, you should be able to figure out example 9. And it's going to be very similar, but there's going to be one little slight wrinkle of assuming that delta is less than 2. Okay. So yeah, that's the cleaner version of example 8, and hopefully you're able to try example 9.